I started recording, so go ahead.
All right.
No. Your Wi-Fi is kind of slim decent.
That's one of the things that they can't figure out.
Okay.
That's the Wi-Fi.
Oh yeah.
Region PC. Yeah.
All right. So we're going to move forward from just like overarching, trying to do threat hunting with PowerShell to being very deep into so feel free to stop and ask a question. Whatever about me, but Joe is he works for a company called Ingame. He's a senior malware researcher. He helped coming up with the technique, and he gave the original presentation with me. So just give him some credit. Overview. So we'll talk about why hunting in memory is really important. A couple of memory-based attacks that are pretty common, and like some new kind of up-and-coming attacks. Existing tools and approaches to solving that problem, and then we'll talk about the tool get injected thread or the script that we released. So so memory resident malware has been basically ubiquitous for the past decade, right? So who here is familiar with Metasploit? Anybody? Yeah, cool. Okay, so Metasploit's like the most popular hacking tool known to man. It's run by a company called Rapid7, but a lot of it is open source. And they have this, they have their rat, or like their implant that they use is called Meterpreter. Meterpreter is a memory resident piece of code, right? And so it gets injected in, and so that's been around for about a decade, and pretty much everybody knows how to use it. Once at one point, this was something that like APT used. Does anybody know what APT means? Advanced Persistent Threats. That's kind of like basically we just want to put somebody on a pedestal, so we act like they're so much better than everybody else. That's what an APT is. But now it's like just generic crimeware, or like pen testers, or everybody's using memory resident malware. The cool thing about detecting memory resident malware is that there's a great signal to noise ratio. So it's we're able to kind of detect it and make sure that it's actually bad pretty easily. All right, so these are the attacker techniques. So we'll start by talking about classic memory injection. So that's if you're familiar with Poison Ivy. Poison Ivy was kind of the one that made classic memory injection famous. Reflective DLL injection, which is what Empire and Meterpreter use. Memory module, which is a different take on reflective DLL injection. Process and module hollowing. And then kind of another technique called PEB unlinking, which is where you change some details about the processes that are running in memory. And then a new technique called gargoyle. So classic injection. If you were to go and say, how do I do code injection on the internet, it's going to come back and give you this list of API calls. So you have open process, which allows you to get a handle to a process so that you can make changes. Virtual alloc x, which allows you to allocate a memory page, so you're able to allocate some segment of memory. Write process memory, which allows you to write data or bytes into that memory segment, and then create remote thread, which allows you to create that thread on a remote system, right? And so we're able to, or on a remote process. And so basically the idea is you're going to take some memory, you're going to allocate some amount of memory, you're going to write code to it, and then you're basically going to create a thread that executes that memory. And so the reason, just to kind of clarify, you have processes, which are applications that are running, but at the end of the day, the things that are executing instructions on the CPU are threads, and so the thread is the thing that's actually running the code in that process. All right, so this is kind of IDAPRO. Is anybody familiar with IDAPRO? So it's a disassembler. It allows you to take a compiled binary or compiled application, and then basically go back and see what the machine instructions that's calling are, so assembly language. And so just to kind of skip through some of the boring stuff, we have the call to virtual alloc, write process memory, and then create remote threads. So this is looking at Poison Ivy, just showing that it does in fact use those calls. We also, when we look at the memory segments, we see read, write, execute memory. The reason why this might be a flag for us is that typically one of the secure ways to do coding is that you're not going to have the ability to read, write, and execute all from one memory segment, right? You may have to read and execute, you may have to write, but usually you don't want one memory segment to be able to be changed, be able to be read and then executed, because then an attacker can basically do all those things. All right. The other thing is this is from I think Process Explorer, maybe Process Hacker, but just showing that typically when you kick off a thread, it's going to be pointing to some API call. When you're using this technique, it's just pointing to some memory address, and so that's one of the kind of detection keys, is that there's no DLL or no file on disk that's implementing the code in this thread. All right, so that's kind of the classic way that we always talk about. But let's kind of move forward to reflective DLL injection, which is kind of the new. Well, it's not really new, I would say, but it's kind of the most popular injection technique. And so this was originally designed by a guy named Stephen Fewer. And so he has a GitHub page where he describes, I think he wrote a white paper originally, and now he's basically describes how reflective DLL injection works. The idea is that from the attacker's perspective, this is like you have a dumb injector. So back with the previous classic injection, you had to write the machine code by hand, and so we call that shell code, which is position independent shell machine or assembly code, right? And so you had to manually craft the assembly by hand and then get it to execute. Well, here you could just take a DLL, inject it into memory, and then they call it doing a fix up of some of the header, and so that it knows how to call everything. And so from an attacker's perspective, you could just take a reflective DLL, load it into memory, and it just magically runs for you. So like I said, Meterpreter and PowerShell Empire do this. So it allocates memory, maps those sections, and then you have to resolve the imports. So imports are the functions that you're going to be referencing, and then fix-ups any relocation. So basically, you have to do a little bit of translation from what a DLL would look like on disk to what it would look like in memory. So this is kind of looking at Meterpreter. Meterpreter has a method called reflective loader, which is basically that DLL being loaded up into memory. Again, you see the read, write, execute memory segments here, and you see the MZ header. So anybody know what MZ header means? No? Okay. So fun fact: all portable executable files, so any application DLLs or EXEs, are going to have the portable executable file form or data structure, which has a signature called the MZ header. And so it's I don't know what his name is, but it was Mark Zubawinski or something like that. I don't know. But he's the guy who created the file format, and so he used his initials to kind of indicate that. So when you're looking for when you're looking at a file, it's always going, or an executable file or DLL or driver, it's always going to start with MZ on a Windows system. And so that we may use that for a detection technique later, right? So if we're looking through and we find some sort of code running in memory, maybe we look for that MZ header to see if that's actually, in fact, an executable file that's executing. All right, so memory module is very similar to the reflective technique, but instead of calling load library, which is allows you to load that library from disk, from disk, you're going to basically implement your own version of load library, which takes a buffer or just a string or a byte array and loads that into memory itself, right? And so very similar technique, but it's just functions a little bit differently. It's a little bit more artisanal, I guess. And typically, they try with memory module to avoid that read, write, execute indicator that we might be looking for. And so here's kind of Net Traveler, which it uses legitimate looking permissions. So you hear you see read and write, or read and execute, or just read, but no read, write, execute access. And so, yeah, so here we have read, write, so on and so forth. We also see, though, that there's no file backing on disk for this, right? And so this is a normal thread, so it's normal thread calling the when HTTP send request method from when HTTP.dll. Here we have 3 threads that are running that are just referring to some place in memory, right? And so why would why would a thread be pointed at some random location in memory instead of at a specific DLL? All right, another one is the WinNTI malware. So that one was not, they were a little sloppy and they left the read, write, execute permissions there. And so that might be an indicator that we're looking for. But what they do that's interesting is they overwrite the MZ header, right, in memory. So they load it up, they execute it, and one of the things that they do once they execute their malware is go back and overwrite that MZ header so that somebody like me is looking for that, it's not going to be there, and that might throw off my analytical process. All right, so this is another cool, anybody know what Stuxnet is? Yeah, everybody knows Stuxnet, yeah. Like my dad knows what Stuxnet is, so, but yeah, like Stuxnet was, who knows who wrote Stuxnet, but it was used in Iran to like mess up with some of their nuclear enrichment or their uranium enrichment facilities, and so they use a technique called process hollowing in Stuxnet to where you load up a legitimate process. So like in their case, in Stuxnet's case, they use LSASS, loaded up a legitimate process and paused execution on that process. They then basically took their code and overwrote all the code and memory of the legitimate process. So that now when I go and I look and I'm like, oh, that's LSASS, it's signed by Microsoft, right? Completely legitimate. I just kind of overlook it. But in fact, LSASS is just a container that's running their version of whatever code they want to run. And so it's a pretty cool method. One of the ways that you could kind of detect process hollowing is maybe compare the code on disk versus the code in memory. And so that might be one way. And so pretty neat methodology. So Dark Comet is another tool or rat that uses process hollowing. And so here, for instance, you see they're creating the process in a suspended state so that the process never actually starts. It just like gets created and then they overwrite everything. So pretty nifty. You see that they have a little bit of read, write, execute, which is where they're committing their code to. And so then you might be able to detect it that way. And then you have module overwriting, which is very similar to process hollowing, which is where you load your process loads a DLL, which it does not need. And so then you can basically load your own code into it, similar to process hollowing. And so when I'm looking and I'm like, okay, why is this thread pointed to some memory space instead of a DLL? You could kind of overwrite that or trick me by having a legitimate DLL that is not implementing its own code, but it's implementing malicious code.
Question?
Yeah.
Where do the names come from? Because as soon as you confirm something, you think this is.
Yeah.
This
so.
Is it's you give the name, the real guys probably don't contact you. Oh, by the way, it's got this.
Yeah. No. Of course. Yeah. So a lot of times the names are kind of derived by the person that found it, right? So like what they'll do is when they're like reversing it. So when you're looking through IDA and you have like this kind of thing, a lot of times there will be like strings that are left over, or like in some cases mutexes, which are like mutexes are used for like shared resources encoding to make sure that multiple threads aren't trying to access the same resource and like crashing your program. And so a lot of times they'll take like the mutex, or like if somebody left in debugging strings in their application, they might say somebody's name or like the name of the project or something like that. And so they try to derive it from something from within the project. Yeah. Or they just, some people are like, this sounds really cool, I'm just going to name it this because that's cool, I guess. I don't know. All right. So here's an example of this Audinoff, which is using the module overriding technique. And so the idea here is this is the PE header. So remember that MZ header. Well, there's a bunch of other information in there. And so now what we're doing is we're comparing what that module or DLL looks like on disk versus what it looks like in memory. And we see that, for instance, the linker version for compilation is different, which is an indicator that something fishy is going on. All right. The next one is PEB unlinking. So when you run like git process in PowerShell, it's pulling all the information, like the location of the file, right? Like so the file path or the command line or even the loaded DLLs in that process. That's all getting pulled from somewhere, and it's a memory structure in memory called the process environment block. And so unfortunately, the process environment block is something that from a normal application you could go in and change change around what that looks like, or like overwrite things or remove links and stuff. And so Hacking Team, we talked about them earlier. They use a technique called PEB unlinking in their RAT, where they unlink references to DLLs that might look suspicious. And so they load up a DLL. So for instance, let's say you don't want your tool to look like it's using the network for communication, because a lot of malicious stuff uses the network for communication. And it might be relatively easy to say like Internet Explorer and like Google Chrome, they should be using the network for communication, but like SVC hosts might not need network communication, or Notepad, for example, doesn't need network communication. And so, but I want to run a Notepad that does have network communication, but I don't want you to know about it. So what I do is I start that up, and then I go back and say, hey, just kidding, we're going to hide this from site so nobody knows that the WinSock DLL is loaded up in a Notepad. All right, and then Gargoyle. So I don't even really completely understand how this works. It's pretty fancy, like new age type stuff. But the idea here is all these other techniques up until this point have had a thread that's associated with it, and it's like in order to run code, you have to have a thread that's executing that code, right? Well, what Gargoyle does is it uses this concept called return-oriented programming, which is typically designed to get around some of the new memory protections like DEP and ASLR and all that kind of stuff. But it's able to like figure out how to asynchronously wake up occasionally, like every, let's say, 30 minutes or day, and then execute its code and then go back to sleep without a thread referencing it. And so it's this super fancy technique that's going to bypass literally everything that we currently know to use to detect memory code injection. So that's the fun one. That's the next thing that I got to work on, is trying to figure out how to detect that. Yeah. So currently there's some tools that you can use. Kind of the most well known is volatility. Anybody here familiar with volatility? So when I talked about power forensics, that's a disk forensics tool set. Volatility is a memory forensics tool set. So what you're able to do is take a dump of RAM from the system, and then they have parsers that allow you to look at all the data structures in memory and pull out information. So they can do things like do rootkit detection. They could also do code injection detection and all kinds of stuff. One of the kind of advantages of memory analysis is that you're doing the parsing offline on memory, and you're not accessing the Windows API, which an attacker can cause to lie to you. And so it's pretty cool. One of the big negatives of memory analysis is it's not scalable. It takes, like, on a system that has 32 gigs of RAM, you have to like dump the memory and then transfer 32 gigs of RAM back to your system, which, like, if you have an office in Hong Kong or something like that, that's going to take forever. And so it may not be the most scalable concept. And so GR and recall is like a fork of volatility that tries to do what volatility does on a live system instead of a dump. And then GR implements recall on the back end to do that. So everything is like volatility, when you're talking memory analysis, is like the granddaddy of them all. It's the main thing. All right, so now we're going to talk about how, like, our process for detecting many of the techniques that I just talked about without Gargoyle and maybe one other. All right, so this is all built on PS Reflect. So who here knew that you could call Win32 API calls from PowerShell? Yeah. Okay. So there's a couple different techniques to do that. One is called platform invoke, which is like the well-known one. If you go to MSDN, it'll talk about platform invoke. And then, like, you use the add type commandlet to compile C# code, which allows you to call APIs, right? The problem with platform invoke is that it does like just-in-time compilation, and so all that data gets compiled, and then you have compilation artifacts that get dropped to the file system. And so we talked about like file recovery and the USN journal and all that kind of stuff. Well, I don't want to overwrite all that information that I might need in my analysis, and so PS Reflect allows us to access all of this information or all these API calls without having to compile code on the system. So it's pretty nifty. It's a little bit more involved than platform invoke, and so it's a little bit tougher to do. But luckily, Matt Graver, the guy who created this, used to work with me, so I have a pretty easy contact with him. So yeah, avoids the compilation artifacts. So it uses a technique called reflection, and what reflection allows you to do is basically access. So the way that we're using, it's called type introspection, the way that we're using reflection. But the idea here is that In C#, when you write code, you can like mark your classes and methods as private, which means that when you compile it and you try to use the functions that the DLL is exposing, the private methods are just for internal use only. They're not supposed to be accessible by some user on the outside. The thing about reflection is it allows you to basically go inside and treat the DLL as if you're executing from within it, right? And so then you can end up accessing these private methods and private classes. Well, C# in general uses platform invoke all over the place, right? Already inside. So a lot of the API calls that we need to access are already implemented somewhere in there. They're just not exposed to us. And so we can use reflection to get back in there and access those. To use PS Reflect, you need the entire code block in there. And so that's like multiple thousands of lines of code in your script. So that's one thing to think about.
Should it be easier to detect them? I mean, if you take some logs or whatever.
Yeah, so I mean, yeah, if you're doing like script block logging, you could definitely detect that.
Yeah, so you could scan for that.
Mm-hmm. Yeah, so I would say that PS Reflect in and of itself is not malicious, because like I'm using it for good, right?
Yeah.
So I don't know that you want to just like detect it and block it per se, but
No, but if you are investigating something.
yeah, sure, yeah. Assuming, yeah, if you have like script block logging, you'll definitely see that. So here we have get injected thread. This is the one that I showed when we detected that Empire module. And so the idea here is Windows has what they call the tool help API. And so that allows you to say, I want to see every thread. So there's an API called thread 32 first, which gives you the first thread, and then thread 32 next, which gives you the next thread. And so you could basically iterate through each thread. And as you're doing that, it gives you the base address of that thread in memory, right? So what code is that thread going to execute? From there, you could then query that code page and say, all right, so we have this code, like this base address for code, so like where that code is located. I want to know, is this code allocated or this memory page allocated? And if it is, does it have a file that's associated with it, right? And so if it is allocated and does not have a file associated with it, then it is going to be almost 100% bad, or it's going to be some security solution that is doing sketchy things in the first place, right? So like an example of something that would be a false positive would be like semantic endpoint protection. They're doing code injection to do some of the things that they're doing. And so while it's not necessarily malicious, it is in fact doing what you're looking for. So it's kind of like a false positive negative thing going on. Yep. So it gives you all kinds of information. When I first was writing this for this presentation, we ended up finishing the code way faster than we thought we would. And so we just kind of like had an extra day or so to like add extra crap to it. And so the things, kind of generic things it gives you are like the process ID, the name of the process, the file path from the process environment block and from the process structure and memory. So remember, we could lie, an attacker can lie to the process environment block, but they can't lie to the process structure. And so then we can compare those two and say, hey, do they match up? If they don't, then something's going on. It also gives you the command line. So then kind of the next level is the thread level. And so you get thread ID if the thread has a unique token. So when you like authenticate on Windows, you're given a token, and that's kind of serves as your persona on the network. Processes all have tokens. So when you say who's like the user running LSASS and it says NT authority system, that means it has an NT authority system token. Well, processes aren't the smallest thing that can have a token. Threads can have a token. And so like in the case of like injecting with Empire into some random process, you can have like a process running as the Alex user with a thread that has system level privilege, right? And so if a thread has higher privilege than the actual process, that's definitely going to be something worth looking into. It's going to give you all the information about the memory segment, so the base address, the size of the memory segment, the protection levels, protection being basic, or the protection level, so that read, write, execute. We can see if it's read, write, execute. State, which is going to be whether it's allocated or non-allocated. And then the type, which is if it's backed by file or not backed by file. And then it'll also give you the first 100 bytes, so you could see if there's like an MZ header or something along those lines. And then it's going to give you the token for either the thread or the process. which will have the integrity level. So has this, earlier he talked about bypass UAC. And so processes, I'm sure everybody knows what the UAC prompt is, right? It's that thing that pops up and says, are you sure you want to run as administrator? And you're like, yes, get out of my way. I'm going to run as administrator. Well, so from a malware perspective, there's a lot of things you can't do if you've never clicked OK, I want to run as administrator. But there's tons of techniques to allow you to basically make that happen or run code under the context of an administrator without ever clicking it, right? And so, for instance, you can see, like, let's say somebody's injected into notepad.exe. Well, notepad probably isn't running as administrator most of the time, but if I have a thread that's running as administrator, but my process isn't, then that's something that might flag me. It also has like the username that the token belongs to, and like the session start time. So when did that user log in? The logon type, so whether it's interactive or network, and the authentication package used. So this one is going to be kind of a quick demo. I know I kind of showed this with Empire, but quickly showing this is really proof of concept. So we run it and show that there's no injected threads. And then Joe wrote this application that literally all it does is inject a thread. And so there we have the thread ID 2756. And then we check get injected thread, and we see that threadstar.exe injected a thread called thread 2756. So this is just like, this is what we used to basically, while we were iterating through the code on this, to make sure that it was actually doing what we expected it to do. All right. So yeah, we look at that. That's cool. At least it works. Now, what about like some real malware that we know does thread injection, right? And so this Trojan, which Palo Alto Networks did a write-up for, so if you're interested in it, there's the little URL down there, or the really long URL that you could go check it out. And so the way that this attack worked is they hosted a zip file on Google Drive, and then they would send emails and say, I think they were attacking people that were going to the Myanmar Industrial Resource Development Symposium, right? And so they would send the contact list that an email that said, hey, there's a PowerPoint slide that you need to check out that's loaded in that's on Google Drive, right? And so somebody would go to Google Drive, download the zip, and then unzip it. And so the interesting thing is, although the file was an executable file, it had the icon of a PowerPoint slide, right? And so, what I'm going to do is I'm going to be like, okay, that looks like a PowerPoint slide. I'll just click on that. And so they'd click it. The executable would run. It would drop out a PowerPoint slide and then open that PowerPoint slide up so that you think that it's working the way that you expected it to, but it's also doing some malicious crap in the background. And so what it would do is it would drop realnetwork.exe, which is actually a legitimate file for I think it's like the real sound driver or something like that. And so that would load up. It's signed by a legitimate company, and then, but it was vulnerable to what they call the DLL sideloading attack, which basically allows, if generally, so there's a lot to it, but generally, if you're vulnerable to the DLL sideloading attack, it means that if a DLL is located in the same directory as the executable file, and it needs to access that file, then it's going to load that file that's located in the same directory first, right? And so what they did is this main.dll, this MPA media.dll was actually a malicious DLL, which they then used to inject main.dll into memory. And so it's kind of convoluted, but ultimately they ended up getting a legitimately signed file to run, but they also ran their malicious code. All right, so let's check out what that looks like. So you see here I have my PowerPoint slide. Looks pretty legit. And of course, nobody has like file extensions turned on by default, right?
Exactly.
Yep. So we click on that, and there our PowerPoint opened. You see, kind of down here, you might have saw the PowerPoint slide get dropped, and the original file got deleted, right? And so, hey, there's our PowerPoint. Looks legit, right? Cool. I'm happy. I just learned about the symposium that I'm going to. All right, so now we run get injected thread, and we have tons of results, right? So there's like four threads that are injected. And so we see, like for instance, it'll tell you the privilege. So like, does this person have SE debug or SE change notify privilege, that kind of thing. We also see that there's this directory inside the user folder, right? So let's go check out that user folder. All oh, hey, there's our real network.exe with our main.dll and all that kind of stuff. And there's that MPA media.dll as well. So now, like, at this point, I would be grabbing those files and like pulling them off so that I could do some like file level analysis. But the interesting thing is that QLES directory is a hidden directory. So they're like attempting to hide from casual sweeps of the directory. And so we were able to detect that. So pretty nifty. All right, so in response to injection, there's kind of a few things that we could do. We could kill the thread, so I showed that with Empire, right? You could just kill off those malicious threads. You may want to do like a process memory dump, and so that's where you dump out the process memory. You could do like Matt Graber wrote out mini dump in the PowerSploit project, which allows you to create a Windows crash dump without actually crashing the system, which is an ideal situation. And then you could use like, I think it's proc dump and sysinternals you could also use. And then you could also do something like, this has not been implemented yet, but like you could dump the thread's memory segment and then like pull that off and maybe see what the code's doing there. All right, so this is like us showing again, stopping those threads and killing them off. So we have process hacker on the left, and we see 4 different threads that we're gonna have to kill off. All right, so let's go down to real network. We could open that up. And I'm on the threads pane here. It's kind of hard to see, but on the left-hand side, you have the thread ID. And so I'm going to start killing off. First one is 920. And you see it turns red and then goes away. And then I just kind of repeat. But eventually you're killing, let's say, so in this case, real network.exe isn't like a critical process. We could just kill the entire process. But in this, like, for demonstration purposes, we're just going to kill off all the malicious threads. All right. And so now we've, oops, didn't mean to click on that. All right, so now we've killed out all the malicious code from the process, right? So like now the legit real network.exe is running even though we didn't need it in the first place. So that's pretty cool.
You need to pipe that, right?
Yeah, so yeah, in theory you should be able to pipe it. I don't think I made it pipelinable. Yeah, I know, I suck. I know, I should. Yeah. All right, calm down. Yeah, so the cool PowerShell-y way to do it would be like get injected thread and then pipe it into kill stop thread. I just failed in this case, I guess. Yeah, sorry.
Something to do on the plane home.
Yeah, I guess. Yeah, I have like a 13-hour flight, so yeah. All right, and so yeah, that's the end of that. Do I have more time? Because I have another like.
Yeah, we still have 18 minutes until
Okay.
we end. How much? 5 minutes? How much do you need to show them?
16 minutes.
Yeah, and I need 30 seconds. So
Okay.
do you have exactly
Okay. Yeah. Sure.
15 minutes?
For you to show us, you want to download, how do I ensure that I get the right version? Because it's very easy for anyone to, of course, if you get it from GitHub, it will be okay, but
Yeah.
then when you link to someone's project, someone thinks it's very easy to inject something in exactly these tools.
Yeah, so I would say even though Matt Graber does malicious code, he now works for Microsoft, so I would implicitly trust him on GitHub. Like even though he does malware, like it's going to be exactly what he says it is. So if he says it's malware, then it's malware. If he says it's okay, then it's okay. Volatility is also on GitHub, but they also like I think they probably give you like hashes that you could compare your downloaded version versus their version. That's probably the best way. But most of the tools that I talked about are on GitHub. So, and like GR stands for Google Rapid Response, and so it's ran by Google. So they're probably
Can't trust that.
yeah. If you don't trust them, then you probably have a hard time computing. I guess.
Like CNN. Like we don't trust CNN.
Yeah. Yep. All right. So I'm gonna end that show. So I have this. This is not related to defense. It's actually more offensive, but it was kind of neat. So somebody had asked the question, if I could find my VM here. Hopefully I have enough time to do this, but
Yeah, sure.
okay. There it is. Okay. So somebody asked the question like, for Empire, they're like, hey, what if like you created a, I don't need this new version, get it here. What if you created like a RAM-based file system, right? So like I could store outputs of things in RAM only, right? And then like access them. And so I thought it seemed like a pretty cool thing. And since I'm talking about memory attacks, might as well show this. And of course, like starting this up is going to take a really long time. Okay. All right, so this is running as admin. Yeah, so I have RAMFS, which is a module that I wrote. And so this is like the PS reflect code that I was talking about. And so we'll see how many lines it is just to kind of get down here. Yeah. Okay, so that's, yeah, there it's like almost 1,000 lines, I guess. So we have a couple different things. So file systems, like I do file system forensics. So like understanding how file systems are structured was kind of my specialty. So it made something like this really interesting to me as kind of a nerdy thing. And so what we do is you could basically do similar things to what they're doing with injection, to where you're saying, okay, I'm going to allocate memory, a chunk of memory, and then I'm going to build the structure of a file system, right? And so there's kind of metadata that goes with it, and then there's actual data. And so this new RAMFS is a function that creates like the file system in memory. And so you could do like process ID. So let's do $p equals get process dash name. We're going to just put in, everybody's always impressed for some reason when you put things in LSASS. So we could do like process.id 604, right? And so now I could do new RAMFS process ID $p.id. And so I'm going to store that in base address. And so now we have a base address, which is the reference to, so you have to know what process you're in, because process memory is all like siloed to where references are all from within the process. But we have the process ID for LSASS, and we have the base address in LSASS for where the file system starts. And so now what we could do is we could do like get RAMFS, let's see, volume header. And so we do process ID. This is something I haven't really played with in a little while, so it's going to take me a second to kind of come up with it as I go. All right, so now what we see, like over here, we see that the like magic signature, you know, there's the MZ header for portable executable format. Well, I'm using garbage file, which is a reference to the Hackers movie, right? If anybody's seen that back in the day. Yep. So and so what we do is we're going to have a pointer to the first file, and then a pointer to the last file, and then the length of each file. And so then each file is going to point to the next file, and so on and so forth, right? And so now we could do like new RAMFS item process ID $p.id. I'm going to get rid of this code here real quick. Okay, base address. So you're telling it again, where is the what did I do? BA. Where is the file system stored? And so like we'll call it or DK, right?
Yep.
Okay. Content, and we're just going to do, it wants like a byte array, right? So we're just going to do 41, which is just AA. So when you translate 41 to like using ASCII, that's going to represent AA for us. And so now if we were to do this again we see that we have the length of the record is 60. So this is pointing to the record, which is going to tell us where the contents of the file are. And then we now have the reference to where that record is, right? And so we could also do like get RAMFS child item. Base address $BA. And so it lists out all of our files. And so like here's our file PSUGDK or UGDK. And so then like this pointer is what's pointing to the file or to the file record, and then the content pointer is pointing to the contents of the file. And you notice that the file is 2 bytes, which is what we would expect it to be, right? And so now we could do get RAMFS content process ID base address $BA file name PSUGDK. And that's all. Oh, we'll just leave it first like that. And we see Remember, this is hexadecimal 41, which if you translate that to decimal is going to be 65. We could also do encoding and do like ASCII, and we see AA. So we just pulled that data directly from memory. And so what you could do is like, as long as you remember, for instance, what the base address is and what the process ID is that's injected into, you're going to be able to recover that at any time, assuming that the process hasn't quit or something like that. So it's pretty neat. Something that we're looking at doing later is being able to put executable code in there and then being able to like use one of our injection techniques to be able to execute that code and run it, which would be neat. So if anybody has any questions, I'll let these guys. Oh.
You can make a PS provider.
Yeah.
It becomes a really
Like a
partial drive.
Yeah. So yeah, unfortunately
for out file and whatever.
Yep. Yeah, that would take me a long time probably because I've never made a provider. But
30 now. It's in
yeah.
progress.
Yep. And then the other reason why provider, so I originally thought about making a provider, but then from like the offensive perspective, you're never going to like install a provider on a remote system. So, but yeah, it would be an interesting project for sure. Yeah. So I'm gonna let these guys take over, but if you guys have any questions afterwards, I'm more than happy to talk about RAMFS. So. Oh, okay. I'll take questions now if anybody's interested. Yeah.
What kind of permissions do you need? I notice you are admin.
Yeah, so you have to be okay, not true. In order to write into a separate process's memory space, you have to be admin. Otherwise, you can only write into your process memory space.
And what are you using there? Are you doing new stuff or writing into existing?
Yeah, so like I've written a bunch of like function stuff. So this is like virtual alloc and write process memory. So it's all like using similar to like the classic injection technique of where you're allocating a memory segment and then you're writing your data directly to it. Yeah.
So you're asking the operating system to allocate memory to your process?
Yeah, and so one of the like key ways to do this on a not a remote process, but on a process that's not the one that you're running out of, like PowerShell ISE, you have to use virtual alloc EX. Because virtual alloc only allows you to deal with your own process. Virtual alloc EX allows you to specify a remote process or a different process. So, but yeah, you can only do that if you're specifically an administrator. Otherwise, you could write only to like your PowerShell. So, yeah, cool. Any other questions? No? Cool. Well, thank you guys for having me. I appreciate it.
Thanks.
I talked to one of the guys, I see he's already left, about the,
Got it. Yeah, go for it.